Welcome back to TAE Certification Training Series. In this session, we will explore the internal TAS metrics. So let's begin. Let's start with our first internal TAS metrics, which is tool scripting metrics. There are many metrics that can be used to monitor automation script development. Most of these are similar to source code metrics for the SUT. In other words, the criteria for measuring automation script quality and the criteria for evaluating the quality of the application being tested share similarities. Lines of code, LOC, and cyclomatic complexity can be used to highlight overly large or complex scripts. Suggesting possible redesign is needed. Let's have a look what is lines of code. Think of LOC as the pulse of your script. Too high and your script might be too complex, so it's time for a redesign. And if it's too low, it might not be comprehensive enough. Then we have cyclomatic complexity. This metric measures the script's complexity based on decision points and the code paths. So high complexity indicates potential maintenance challenges. Next, we have the ratio of comments to executable statements can be used to give a possible indication of the extent of script documentation and annotation. So what is ratio of comments to executable statements? It's a measure of how many comments or explanations exist in your code compared to the actual lines of code that do something, or as it's referred over here as executable statements. And a high ratio suggests well annotated scripts that are easier to understand and maintain. Then we have the number of non-conformances to scripting standards can give an indication of the extent to which those standards are being followed. Okay, let's have a look at this now. Picture your script as a puzzle. Non-conformance to standards is like trying to put pieces from different puzzles together. And what will happen? It won't just fit. Following standards ensures that all the pieces align. So in the world of automation scripts, these metrics serve as valuable tools for ensuring the reliability, efficiency, and maintainability of automation scripts, which then improves the overall quality of the automated process. Number 2, automation code defect density. Code defect density is a metric that measures the number of defects or issues in a section of code. It helps to assess the quality and reliability of the software by quantifying the density of defects. Automation code is no different than the code of the SUT in that it is software and will contain defects. This means that just like the main software you are testing, which is SUT, automation code is also a software and can have errors or bugs. It's essential to recognize this similarity. Automation code should not be considered less important than the SUT code. Okay, so do not underestimate the importance of your automation code. It's as crucial as the SUT code. It plays a vital role in ensuring that your testing processes run smoothly. Good coding practices and standards should be applied, and the result of these monitored by metrics such as code defect density. You should follow best coding practices and standards when writing automation code. Metrics like code defect density can help you track of how well you are doing in terms of your code quality. These will be easier to collect with the support of a configuration management system. Using a configuration management system can make it easier to gather and manage these metrics, helping you keep your automation code in good shape. It's like having a toolbox to help you measure and improve your code quality. Number 3, speed and efficiency of TAS components. Differences in the time it takes to perform the same test steps in the same environment can indicate a problem in the SUT. Inconsistent timing can be a red flag. For example, if a login process takes significantly longer at times, it might indicate issues with the system's performance or reliability. Then we have if the SUT is not performing the same functionality in the same elapsed time, investigation is needed. So investigating these time variations is essential to ensure the reliability and performance of the application. Next point is this may indicate a variability in the system that is not acceptable and one that could worsen with increased load. So these variations could signal let's say a performance problem in the system, and this can be significant during periods of heavy usage. Next, the TAS needs to be performing well enough for it not to hinder the performance of the SUT. So if we take the example of login, the TAS should not slow down the login process, but actually it should support its performance. And lastly, we have if the performance is a critical requirement for the SUT, then the TAS needs to be designed in a way that takes this into account. So if the speedy logins are crucial, if we take our login example, then the TAS should be designed to work seamlessly with the system to ensure efficient login times. And at the end, we have trend metrics. With many of these metrics, it is the trends, that is the way in which the measures change over time, that may be more valuable to report than the value of a measure at a specific time. This means that for many metrics, what's most important is not the individual value of the metric at a single point in time, but rather how that value changes over a period. In other words, it's often more valuable to observe and report the trend or pattern in how a metric evolves over time. Let's have a look at the given example. Knowing that the average maintenance cost per automated test requiring maintenance is more than it was for the previous 2 releases of the SUT may prompt action to determine the cause of the increase and undertake steps to reverse the trend. Okay, so to understand this example, let's have a look at this graph. So over here, you will see that the average maintenance cost is shown for different releases. For release 1, it's quite low. Then it's for the release 2, it's really high. Then release 3 is slightly low. And then we can see an upward trend. So we can see that this trend indicated by the rising line on the graph is like watching your monthly utility bills gradually increase. In the context of the example, it's the growing cost of maintaining automated test. This upward trend would prompt you to investigate and determine why the costs are rising. Are there any new issues or complexities in the software that make test maintenance more expensive? Then we have the cost of measuring should be as low as possible, as this can often be achieved by automating the collection and reporting. Okay, so for example, in the context of tracking software maintenance cost, manually collecting and reporting this data might be time consuming and prone to errors. However, by automating the process, you can reduce the time and effort required, making it more cost efficient. Automation can help ensure that the data is consistently and accurately collected and reported, saving both time and resources in the long run. We have now completed our section 5.1, and in our next session we will start exploring section 5.2. Until then, take care.